Hello. Now we are going to look at transversals and similar triangles. And we're going to start with just some facts about triangles. In any triangle, the largest angle must be opposite the largest side. And as a continuation of this, the smallest angle would be opposite the smallest side. And we'll look at that in practice in a minute. The next idea we want to talk about is similar or equiangular triangles. So similar and equiangular mean the same thing. Similar is the word we will most often see for these triangles, but equiangular is nicer because it tells us what we mean. Equi means equal and angular means we're talking about angles. So similar triangles have the same angles in them. So they're two separate triangles that have the same angles in them. If we take our two triangles down here, we have this angle is the same as this one, it has the same symbol, and likewise for our other angles in here. So these are two similar triangles. They are equiangular. They have the same sized angles in the same relative positions, so they're similar or equiangular. Now, similar or equiangular triangles have a very useful property because they're effectively the same shape, just zoomed in or out. That means that they scale the same. So this isn't quite true for the size of diagrams I've drawn, but if we took the side E here, if we said that E was going to be twice as big as B, B is the side that would be in the corresponding or the same relative position as E. It's across from the single dotted angle. So that's how it's in the same relative position or the corresponding position in both triangles. If E was twice as big as B and they're similar triangles, because the proportions of all of these sides are the same, we would be able to say that D would be twice as big as C and F would be twice as big as A. They're all in the same ratio is how we say it mathematically, but it just means that if E is twice as big as B, we automatically know that D is twice as big as C, and so on. So that's what is useful about similar triangles. The sides are in the same ratio. So in my example, E was twice as big as B. So this ratio here would be 1/2. It would be a half. So this triangle's sides would be half as big as the bigger triangle's sides. That's not quite true for this picture, but that's a way that we can think about it. Now, the other idea we need to deal with is connected to our similar triangles, but it looks a little bit different initially, and it's transversals. So this means that we are crossing a bunch of parallel lines. So we have lines going across several parallel lines. I know these orange lines are parallel because they have the little arrows in them that tell me that I have parallel lines. And I have a line L that I have in blue here, and when L is crossing our parallel lines, it gets cut into equal pieces. The 3 units long here and 3 units long here. And I have a little dash that tells me that the lengths are the same. Well, it turns out that where you have parallel lines moving like this, and you have transversals, you have lines transporting across or moving across those parallel lines, the way that they get cut up is always going to be the same. So because these were cut into 2 equal pieces, I know that the line K, even though it's going at a different angle across my parallel lines, it's going to get cut up in the same ratio as well, cut up in the same sized pieces. So if this length here was 4, and I don't know this length, I know K must be 4 as well, because it must get cut up into 2 equal pieces if L got cut up into 2 equal pieces. And whatever the ratio was here, so say if this length here was 3 times this length here, then this length here would be 3 times this length here. So the ratio is always the same when we're crossing our parallel lines. So I automatically know that K must be 4 because L got cut up into equal pieces, K must get cut up into equal pieces. So that's our transversals. Now let's get into some application type stuff. So a triangle has sides 10 units, 16 units, and 14 units, and it has angles 80 degrees, 60 degrees, and 40 degrees. Now I should stress, these are very approximate angles to make this easier to write down. This triangle can't technically exist, but if we round our numbers nicely, it makes it easier for us to write down an example. But strictly, these angles and sides don't work. But for our purposes, how would we be able to draw a rough approximation of a triangle like this? Well, we go back to the first thing that we thought about today, which was that the largest side must be across from the largest angle. So I know my biggest side of 16 must be across from my biggest angle of 80. I know my smallest side of 10 must be across from my smallest angle of 40. And I know my middle side must be across from my middle-sized angle. So the first thing I would do is not make any attempt to keep the sides correct. I'd just draw something like a triangle, and I would put in my angles. This is just a very crude quick sketch. So 80, 60, 40, and where would the different sides have to go? Well, across from the 80-degree side, I'm going to put my biggest side of 16. Across from the 60-degree side, I'm going to put my middle side of 14. And across from my smallest angle, I'm going to put my smallest sized length. So now I can visualize roughly what this has to look like, and now I might try and draw a bigger diagram. This was just a very crude sketch to give myself a feel for what's going on. Now I might try and actually draw this a little bit more proportionally. Make sure the 10 is indeed smaller than the 14, is smaller than the 16. So I'm going to draw that out a little bit more neatly now. So when I have that drawn in, I have deliberately made it that this side is a little bit smaller than this side, is a little bit smaller than this side, and then I labeled in my angles appropriately. This is only a very crude sketch. I've deliberately left it freehand drawn just to highlight that fact. But if we're asked to do a basic sketch of a triangle, or at least to understand where our angles and sides would relate to each other, this type of activity can be helpful. Our final point on general facts about triangles for now is going to be, if we look at the side 16, the other two sides of the triangle, to form a triangle, must be able to add up to a bigger length than 16. If we think about what would happen if the lengths were smaller, so if I just draw in something very crude here, if I had a side length of 16 for a triangle, and then I said that I had a side that was 5 units long going this way, and I had a triangle that was 5 units going that way, well, they wouldn't be able to reach this length, and this length is not far enough to reach across 16 units. So they can't possibly meet up and form a triangle. So anytime I have a triangle, I know that any of the sides must be smaller than the other two side lengths added together. Otherwise, the other arms, the littler arms, wouldn't be able to reach out and meet to form a triangle. So this is just a fact that we can be asked about, that our arms have to be able to meet each other, and mathematically that means that if we add the two other side lengths together, they always have to be bigger than the third side length for any triangle. Now, if we have a look here, this is kind of a combination of similar triangles and our transversals, and it's the ratio of sides where we have our triangles cut up by parallel lines. So I have two parallel lines here. I have my triangle broken up. So the rules I learned about for transversals and for similar triangles apply here. I have a little triangle here, and I have a bigger triangle, and those two triangles must be similar to each other because they have to have the same angles. I know these are corresponding angles, these are corresponding angles, this is a shared angle. So I have similar triangles, or I can also think about it as having transversals, and the logic will work out the same. How would I use the fact that I know I have transversals or similar triangles to find my missing sides of x and y? Well, I know that the ratios of the sides are going to be the same for my similar triangles, or how the sides get broken up by my parallel lines would also be the same. The ratios would be the same. So if I look at my side length x here, and I look at the other sides in my triangles, I have this length from here to here is 4 units, and this length from here to here is 2 units. So the ratio of this length here to this length here would just be a half, or it would be 2 over 4. Well, the ratio has to be the same here, so x over 6 has to be the same as 2 over 4. The ratio must be the same. X over 6 must be equal to 2 all over 4. So you can simplify that fraction down. You end up with x all over 6 must be equal to a half. Multiply both sides by 6 to get x by itself, and x must be 3. So because the ratios are the same, we're able to work this out. How would we do this for y? For y, we're comparing this little side of the smaller triangle to the complete side of the bigger triangle. So I need to now compare the total length here, which is 6, 4 and 2 is 6, to my smaller side that I'm comparing to. So for that, I would have the smaller side of my triangle here compared to the total bigger triangle would be 4 over 6, or smaller to, we'll do bigger to smaller because we're doing y, so 6 over 4, and we would have y over 2 must be the same ratio. So if I write that in, I know that y all over 2 must be the same as 6 all over 4. If I multiply both sides by 2, or by, yeah, we'll just do it by 2, and simplify to get y by itself, we will end up with y being 3. When we put it into our calculator. So we have the ratios of the sides must be the same because they're similar triangles, or we can use the same argument for transversals. Either way, because the ratios are the same, we're able to work out the sizes of x and y. Now we can do that here again. We can see that we have similar triangles in this case because we have symbol for a right angle down here, and we have 2 dots here and 1 dot here. So the angles are all the same in the same relative positions. So we have similar triangles. The ratios of the sides must be the same. So if I wanted to find this side A, I know that A has a corresponding side of 4, and 15 has a corresponding side of 5. They're in the same relative position. So A all over 4 must be equal to 15 all over 5. Well, 15 over 5 is just 3. So A all over 4 must be equal to 3. Multiply both sides by 4. And A must be equal to 12. I should write that in on my diagram once I know it. Just like I should have for x here. I forgot to do that. So x being equal to 3, we'd put in once we found x, and it might help us find y. And then finally we need to find C. So C is in our smaller triangle, so I need to make sure my ratio is the right way up. C has a corresponding side of 9, so what would C over 9 be the same as? Well, that would be the same as 5 all over 15 or 4 all over 12, either would work. But we'll just use 5 over 15. Well, that's going to be a third, because we're going in the opposite direction. So this triangle is 3 times, the side lengths are 3 times the size of this for all our sides. So going back the other way, it'd be a third of the size. So we need to multiply both sides by 9 in order to get C by itself. So we end up with 45 all over 15. So you end up with 3. So that's how we can use our ratios from our similar triangles, or the idea of transversals in our upper question here, to find missing sides in our triangles. And that is what we need for now.